So on the periodic table that I provided, you have what we call the electronegativities. Remember, they get higher as you go up toward fluorine. So this is 4.0, 3.5, 3.0, so on and so forth. Those electronegativities tell us how the nucleus of the atom, how strongly it attracts electrons. If it is 4, it attracts electrons pretty strongly. And if it is bonded with another atom, then it's going to pull those electrons over closer to it. So this is like kind of like a electron selfish number. Like how much, what are you doing? Get some glasses on.
I'm not on the highway.
So if we take a look, those electronegativity numbers are here as well. Well, the electronegativity difference, we take those two numbers and we find the difference. So fluorine has 4 and carbon has 2.5. So the difference there is 1.5. So we have 3 classifications. If it's 0.4 or less, it's nonpolar. If it's 0.5 to 1.9, it's polar. And if it's greater than if it's 2 or greater, then it's ionic. And what does each of these mean? Nonpolar would be an equal handshake. Equal sharing. The electron pairs are basically equal between the two atoms. Polar covalent is selfish. And the one that wins out on this is the one that has more electronegativity. So that's why you see this arrow pointing towards the F, because these electrons are being pulled closer to the F. So it's like that weird uncle or whatever, whenever they shake your hand, for some reason, they seem like they have to pull your hand away from you, right? Guys may be able to relate with that. But I mean, like whenever you go to shake somebody's hand and they're like, ha, 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 and try to pull it away, or if you've ever seen, what is it, former President Trump. That weird selfish handshake thing, right? Let's see if we can find a decent video. Because I usually actually do this with the kid and I play the weird uncle. Like the pull the thing. Ta-da. Wouldn't have any sound. Oh, I've got the ad muted. That's okay with me. Spaghetti. Man, this ad is long. Is there a better video?
Here comes the.
Oh, we can skip it right. Oh, wait. Dang it. It's not what I wanted. Come on, get off there. There we go. Let's take a look, see how he pulls it closer to him or whatnot. That's kind of what these things are doing. Pulling the electrons closer. They're greedy in a sense because of that high electronegativity. But that's the idea there. Higher electronegativity you have, the more attractiveness you're going to have towards those electrons, the less equally you're going to share them. And here's the kicker. If you're greater than, if you're 2 or greater, that's whenever you sit there and say, okay, I'm not really sharing with you anymore. I'm just going to take this. So it would be like a handshake where somebody just cuts off your hand and then walks away. That's ionic, right? That's a full transfer. Kyle, have you ever had anybody do that to you? Nobody's ever cut off your hand and taken it? No, no, no. How about the uncle or the overly aggressive friend that's like when they shake your hand, they pull you off your balance? Just depends, but somebody has done it, right? Yeah. What's that? You flip over, you take off your t-shirt? You do what? Oh, you put their picture on a t-shirt and say, don't shake hands with this guy. Yeah, right? Public embarrassment. Just, just has it. So again, non-polar covalent is an equal sharing of electrons. Polar covalent, they're pulled toward the more electronegativity atom, and ionic, a transfer of these electrons. So if we were going with boron and hydrogen, we have 2 and 2.1. So the electronegativity difference, that just means we subtract the 2 and its absolute value, we get 0.1. So that lines up with non-polar covalent. Oh, covalent. So that's just a regular old bond. 2 atoms of the same type, well, you're going to get 0 for your electronegativity difference, and that would be non-polar covalent. Carbon and hydrogen, 2.5 and 2.1. Well, we get right on the cusp. They're a little bit closer to the carbon, but not enough to see any difference. So that's still non-polar covalent. Also, arsenic and sulfide, that's 0.5. That's barely polar covalent. So that means that these electrons are going to be pulled ever so slightly more towards sulfur. So sometimes you might see this represented as a plus sign on the arsenic and an arrow pointing towards the sulfur there. Other times you might see somebody put a lowercase delta on both of these. And basically that tells us that there's a partial negative charge here and a partial positive charge here. Tin and fluorine, the difference there is 2.2. So we are above 2. So this is ionic. That means that fluorine has taken the electrons away from tin. So instead of being partially charged, we have a full negative sign and a full positive sign. And these two are attracted to each other by an ionic bond, meaning that the electrostatic charge, the positive and the negative, forces those together. But that's how you figure out if a bond is polar or nonpolar or ionic. You've got to find the difference in electronegativities, compare it to this chart. But what does that mean as a molecule as a whole? So we know that water, H2O, has this right here, Lewis structure. So let's see if we can find. It's a special kind of water fountain that's kind of cool. I can't think of the name of it. What is it? Lime? Linear something? I can't think of the name of it. Oh, laminar flow. Have you guys heard of this laminar flow? Let's take a look at laminar flow. Video on it. So water holds itself together. We know this because water is in droplets. We know this because when water pours out of a faucet, it kind of stays together. If you've ever been in the shower and let's say you stick your hand out or something like that, the water will trickle down in kind of a path, and you'll see it on your, it'll stay in this like trend. These aren't very good ones. Let me get rid of that. And let's just look at the ones in Detroit. And apparently I've looked at this one before.
Okay, check this out. I'm at the Detroit airport, which is pretty much like the future. And they have a laminar flow fountain that I love.
Take a look. What laminar flow does is it forces the water to be in like one direction. But see how the actual water is sticking itself together. That's based off of a property known as this polar bond system that we have here.
How cool is this? Pop jets. There's my wife. Just letting me do my thing. That cool.
So if you were to look at this up close, you almost, let's see which one, this guy right here might have it. You almost can't really see that there's any movement at all.
Grammarly can help you write quickly and confidently, so you never have to slow down at work.
Hey guys, welcome back. I'm Nate with the King of Random, and today we're going to build a laminar flow nozzle. Laminar flow refers, looks really good. Let's seal this thing up and make all of the connections permanent. All right, as an update, we've done
So he shows you how to create one of these if you're interested.
amazing how clear.
But see how that looks like it's perfect almost, and it's all stuck together. Let's see what he ends up. Right here.
Stream does start to get a little bit wonky, and I know one of the reasons for that is higher pressure, especially out of a garden hose, is a little less consistent. I have plans for the future to look into what I can do to make it so that we have more consistent.
But you can actually get this if you have a high enough pressure that you could get this to almost look like one continuous physical thing. Pretty cool. So let's look at what the actual structure of water has to do with making this look like this. Well, if we take a look, here is the Lewis structure for water, H2O. When we do these bonds, we have an HO bond. If we take a look here, the electronegativity difference 2.1 to 3.5. That is an electronegativity difference of 1.4, right? Now, when you're doing a whole molecule, you have to do every bond. But that's easy for this because the bonds are the exact same. So it's 1.4 for each one. Where does that fall in? Well, that falls into polar covalent. So that means that these bonds are polar covalent. The higher electronegativity is at the oxygen with 3.5. So these bonds here are going to be pulled closer to the oxygen. What that's going to do is that's going to give us top right here an overall negative charge, but partially. And this bottom here, we're going to have positive charges. Well, what will happen then is another water molecule right next to it will be attracted to that partial negative part of it will be attracted to the partial positive of another one. And then this will keep happening, so on and so forth. You have a big connection here. This one's attracted to this one's attracted to this one. And over here, same thing. This one's attracted to this one. And then we'd have another one attracted here, so on and so forth. This is what causes water to create droplets. What causes water to come in streams. This is what causes water to be able to make those fountains like we saw. All of these things are possible because of this polarity. And we would say that since there's an overall pull in one direction for the electrons, that this is a polar molecule. The molecule as a whole is polar. So the second part of this lesson is determining whether something's polar or not molecule-wise. The first thing we've got to do is find out whether bonds are polar. So one, are there polar bonds? If there are no polar bonds, then it's nonpolar, and it won't have these attractive forces like water. So that's the first question. Let's take a look here. SO2. Well, we've got to be able to draw that. Who's in the center of SO2? Sulfur. Oxygen there and oxygen there. So if we take a look, sulfur gives us 6 electrons and oxygen gives us 6 each for a total of 12. That's 18, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Well, we're showing 20 electrons, which means we need a double bond. Anytime we make a double bond, we take away a pair of electrons from each atom involved. Well, this could also be showing resonance. So I'm going to go ahead and draw the second structure with resonance. The shape of this is a little bit misleading because I've drawn it out straight. In reality, it's bent because we have 2 bonded atoms and 1 unshared pair. So I'm going to take and redraw this over here one time, just so I can see that awesome bent shape. So I'm going to determine if these bonds are polar or non-polar. So we come over here. Sulfur is 2.5. Oxygen is 3.5. So what that means is these are polar, and they're going to be pulling towards the oxygen. So since there's pull down and to the right and down and to the left, and there is no upward pull, this is polar. So this would stick together, these molecules would stick together like water. Now this thing is huge. If it's polar, it tends to have a higher boiling point. And stuff like that. So this polarity thing is a big, big thing as to how the world around us exists. Now, keep in mind, I said, well, are there polar bonds? If they're polar bonds, it doesn't necessarily mean 100% that it's polar, because do they cancel? These do not cancel. You have things pulling down to the left and down to the right. So left and right may cancel each other. It's the down problem that makes this polar. There is no pull up. If there was a pull up, then all 3 of these would cancel and we would have non-polar, but this is polar. Let's try CH4. So a little thing about this is tetrahedral in arrangement. We said that the CH bond is non-polar. So does this contain non-polar polar bonds? No. So this automatically, since there are no polar bonds in this, it's automatically non-polar. Let's jump down to 6. This time, instead of H, we have F. This is also tetrahedral, and the electronegativity difference between C and F is 1.5. So that's 1.5, 1.5, 1.5, 1.5. We have polar bonds. So this has the chance to be polar. The problem is it's tetrahedral in arrangement. So there's a pull that way, a pull that way, a pull that way, and a pull that way. All of these different pulls are going to cancel out the rest of them. So if they cancel out, let's take a look at what tetrahedra looks like. We have a pull this way. Let me zoom out a little bit real quick. We have a pull this way and this way and this way and this way. So those are all going to cancel each other out. And since they cancel each other out, it's non-polar. And keep in mind, when we do this, we have to look at every single bond in the molecule. If the molecule has polar bonds, it has the ability to be polar. If they don't cancel each other out, it's polar. If they do cancel each other out, it's non-polar. So I'd like for you to use the rest of the period to do the rest of these. 1, 2, 3, 4, 5, 6, 7 problems. If you have questions, by all means, stick around afterwards. Otherwise, have a great day.